Look up into the velvet blackness of a clear night sky. What you are witnessing is a spectacle of profound deception. Each pinpoint of light, each distant galaxy, is a testament to matter, to energy, to existence. For millennia, we believed this was the grand stage of reality. We charted these constellations, we measured the light from these stellar furnaces, and we constructed our theories of the cosmos based on what we could perceive. We thought that by cataloguing these luminous islands in the great cosmic ocean, we were mapping the universe in its entirety. We were, it turns out, profoundly and humblingly mistaken. The stars, the nebulae, the magnificent spiral galaxies, all the things that shine, are merely the foam on the crest of an impossibly deep and invisible wave. They represent an almost trivial fraction of what is actually out there. Our entire perception of existence has been limited to a sliver of reality, a mere 5% of the total cosmic inventory. The rest, the overwhelming 95%, is a domain of shadows. It is an empire of invisibility, a substance and a force that do not emit light, do not reflect it, and do not interact with our instruments in any conventional way. This is the true universe, the dominant reality that has shaped our cosmos from its first moments. It is a universe hidden in plain sight, its presence inferred only by the subtle gravitational dance. Of the things we can see, this is the story of the dark side of the universe. Our first trembling steps into this unlit territory were taken not in some modern high-tech observatory, but in the mind of a brilliant, cantankerous, and visionary astronomer in the 1930s. His name was Fritz Zwicky, a Bulgarian-born scientist working at Caltech, a man known as much for his abrasive personality as for his staggering intellect. Zwicky was a thinker of ferocious originality, often decades ahead of his contemporaries, a fact that frequently left him isolated and his ideas dismissed. He possessed a unique intuition for the workings of the cosmos, an ability to see past the obvious. In 1933, he turned his attention to a colossal congregation of galaxies known as the Coma Cluster, a swarm of over 1,000 galaxies bound together by their mutual gravitational pull, located some 300 million light-years from Earth. He set out to do something that was, in principle, quite simple: weigh the entire cluster. His method was ingenious. He knew from the laws of physics that the faster the galaxies on the outskirts of the cluster were moving, the more total mass there must be at the center, its gravitational influence acting like an anchor, preventing them from flying off into the intergalactic void. Imagine a child swinging a ball on a string around their head. The faster the ball whirls, the stronger the child must pull on the string to keep it in orbit. The speed of the ball reveals the strength of the pull, and in the cosmos, the strength of the pull is a direct measure of mass. Zwicky painstakingly measured the velocities of several galaxies within the cluster. He then performed another calculation, estimating the cluster's mass based on what he could see. He counted the number of galaxies and, based on their brightness, estimated the total number of stars they contained. This gave him a mass based entirely on the luminous, visible matter. When he compared the two results, the discrepancy was not small, it was breathtaking. The galaxies were moving with such astonishing speed that there should have been nearly 400 times more mass present than what was visible in all their stars combined. The celestial anchor was far, far heavier than it appeared. The cluster was behaving as if it were saturated with some unseen, non-luminous substance. Zwicky, in his characteristically blunt style, called this missing component dunkel materia, or in English, dark matter. It was a revolutionary, almost heretical idea. For the scientific community of the time, it was a step too far. Zwicky's calculations were largely ignored, dismissed as a strange anomaly, perhaps an error in his observations, or a misunderstanding of galactic dynamics. The astronomical world continued on its well-lit path, comfortable in its assumption that the universe was made of the same kind of atoms that constitute our planet, our sun, and ourselves. The darkness Zwicky had glimpsed would have to wait in the wings of scientific thought for decades, a ghost haunting the periphery of cosmological models, waiting for its moment to reappear. That moment arrived 40 years later, not in a vast cluster of galaxies, but within a single one. The work was carried out by an American astronomer named Vera Rubin, a tenacious and meticulous scientist who had fought for her place in a field largely dominated by men. Rubin was not looking for missing mass. Her goal was to precisely map the motion of stars within our neighboring galaxy, the Great Spiral of Andromeda. Working with her colleague Kent Ford, she employed a sophisticated spectrograph to measure the rotational speed of stars at various distances from the galaxy's core. The prevailing expectation, based on Newton's and Einstein's laws of gravity, was simple and elegant. Just as in our own solar system, where the innermost planets like Mercury race around the Sun, while the distant worlds like Neptune crawl along at a far more leisurely pace, it was assumed that stars at the visible edge of Andromeda would be moving much more slowly than those nestled close to the bright, dense galactic center where most of the visible mass resides. The gravitational pull should diminish with distance, and so too should the orbital velocity of the stars. The graph of this expected motion, the galactic rotation curve, was predicted to rise sharply near the center, and then fall off gracefully towards the periphery. To visualize this, picture a spinning vinyl record. A point near the center label travels a very short distance with each rotation and moves slowly. A point on the outer edge must travel a much larger circumference in the same amount of time, so it is moving significantly faster. Now, a galaxy is not a solid disk. It is a collection of individual stars held by a central gravitational source. It should behave more like our solar system. Vera Rubin prepared to chart this elegant, predictable decline in stellar speed. What her data revealed was anything but predictable. It was utterly, fundamentally wrong. The rotation curve did not fall. After an initial rise, it flattened out into a perfectly straight line. The stars on the farthest, dimmest edges of the Andromeda galaxy were orbiting at the exact same blistering speed as stars much closer to the center. This was a physical impossibility. It was like discovering that Pluto orbits the Sun at the same velocity as Earth. The only way this could happen is if the galaxy was not what it appeared to be. The visible disk of stars, the beautiful spiral arms, were just the luminous centerpiece. The galaxy had to be embedded within a gigantic, invisible sphere, a halo of unseen matter that extended far beyond the visible edge, its gravitational influence gripping those outer stars and whipping them around at incredible speeds. Rubin and Ford were stunned. They checked and rechecked their data. They observed other galaxies, and then more still. The result was always the same. Every single spiral galaxy they examined showed this bizarrely flat rotation curve. The conclusion was inescapable. Zwicky had been right all along. Galaxies were not just islands of light. They were luminous tracers embedded in colossal, spherical clouds of dark matter. This substance, this mysterious gravitational scaffolding, was not a rare anomaly found only in massive clusters. It was a fundamental and ubiquitous component of every galaxy, including our own Milky Way. The ghost that had haunted cosmology for 40 years had finally materialized, not as a visible form, but as an undeniable gravitational presence. The hunt for its identity was about to begin. The evidence was now overwhelming, but the central question remained a profound enigma. What is this stuff? The universe's most abundant material was a complete mystery. Scientists embarked on a cosmic detective story, proposing a list of potential suspects. The first and most intuitive category of candidates was something astronomers called MASHOs, an acronym for Massive Compact Halo Objects. The idea was that the missing mass wasn't some exotic new particle, but was simply composed of ordinary matter that was difficult or impossible to see. This could include things like cold, dead stars known as brown dwarfs, stars that failed to ignite, or isolated black holes and neutron stars drifting silently through the galactic halo. Perhaps there were countless rogue planets, ejected from their solar systems to wander the darkness alone. All these objects are made of the same protons, neutrons, and electrons as us. they just don't shine. It was a plausible, conservative theory. But how could one possibly detect a swarm of invisible objects spread across the vastness of a galactic halo? The answer lay in a subtle prediction of Einstein's theory of general relativity: gravitational microlensing. Einstein had shown that massive objects warp the fabric of space-time around them. This curvature of space-time acts like a lens, bending the path of light that passes nearby. If a Mako, a dim brown dwarf, for example, were to pass directly between Earth and a distant star, its gravity would momentarily act as a magnifying glass. For a brief period, the distant star would appear to brighten significantly and then fade back to normal. As the invisible object continued on its journey, it would be like searching for dark cannonballs scattered across a vast field by looking for the fleeting distortions they create in the image of the blades of grass behind them. Several ambitious projects, like the Mako project and OGLE, were launched in the 1990s. They monitored the brightness of millions upon millions of stars in neighboring galaxies night after night, patiently waiting for these telltale brightening events. They did find some. The theory was proven to be correct in principle. Microlensing events were detected. However, they were far too rare. After years of meticulous observation, the surveys concluded that, while some Makos certainly exist, they could only account for a tiny fraction, perhaps 20% at most, of the total dark matter required to explain the galactic rotation curves. The primary culprit was still at large. The darkness was not made of familiar things hiding in the shadows. It was something else entirely, something new. With ordinary matter largely ruled out, physicists turned their attention to a more exotic class of suspects: the subatomic and the theoretical. The leading candidate that emerged from the world of particle physics was a hypothetical particle, known as the WIMP, which stands for Weakly Interacting Massive Particle. The theory proposed that in the hot, dense soup of the very early universe, a vast number of these heavy particles were created alongside the protons and neutrons we know. The key to their nature lies in their name. Massive explains why they have such a strong gravitational pull, forming the halos that hold galaxies together. Weakly interacting explains why they are so maddeningly difficult to detect. This term refers not to their gravitational influence, but to their relationship with the other fundamental forces of nature. They do not feel the electromagnetic force, which is why they don't emit, reflect, or absorb light. They are truly dark. They also don't feel the strong nuclear force, which binds atomic nuclei together. This means they would pass through ordinary matter through walls, through our bodies, through the entire planet Earth, as if it were almost entirely empty space. A WIMP is the ultimate ghost particle. Billions of them could be streaming through you every second, without leaving a single trace. But weakly interacting is not the same as non-interacting. Very rarely, on an almost improbable basis, a WIMP should collide directly with an atomic nucleus of ordinary matter, like a ghostly billiard ball striking a physical one. This collision would be incredibly subtle, causing the nucleus to recoil and release a minuscule flash of light, or a tiny vibration. The challenge was to build a detector sensitive enough to register such an ethereal event and to shield it from every other possible source of cosmic noise. This led to the construction of some of the most remarkable experiments on Earth. Scientists descended deep underground into former gold mines and road tunnels to use the rock of the planet itself as a shield against the constant rain of cosmic rays from space that would otherwise swamp their delicate instruments with false signals. In these subterranean labs, they built detectors of extraordinary purity. Experiments like the Large Underground Xenon, or LUX, detector in South Dakota, and its successor, Xenon 1T in Italy, consist of massive vats filled with tons of ultra-pure, liquid xenon cooled to incredibly low temperatures. The entire apparatus is then submerged in a larger tank of purified water, adding yet another layer of shielding. The interior of these detectors are among the most radioactively quiet places in the known universe. For years, teams of physicists have sat in control rooms, watching, waiting, They are hunting for a flicker of light in the heart of the xenon, the signature of a single WIMP bumping into a single xenon nucleus after a journey of billions of years across the cosmos. It is an endeavor of monumental patience and technological prowess. Despite decades of searching, and despite building ever larger and more sensitive detectors, we have not yet found definitive, repeatable evidence of a WIMP collision. The silence from these deep underground chambers is becoming profound. While the WIMP remains a compelling candidate, the lack of detection has prompted theorists to explore even more unusual possibilities, like the ultralight axion particle or the concept of sterile neutrinos. The darkness remains stubbornly persistent. We have mapped its shadow across the cosmos. We have felt its gravitational grip on the stars, but its true form continues to elude our grasp. And as this perplexing search was deepening, the universe was preparing to reveal that its dark side was even more vast and more bizarre than anyone had ever imagined. By the mid-1990s, cosmology had settled into a comfortable, if incomplete, picture. The universe was expanding, a fact known since the work of Edwin Hubble in the 1920s. This expansion was thought to be constantly fighting against the inward pull of gravity from all the matter within it, both luminous and dark. The biggest question in cosmology was the ultimate fate of the universe, and it all depended on a cosmic balancing act. Was there enough matter, enough gravitational pull, to eventually halt the expansion and cause the cosmos to collapse back on itself in a big crunch? Or was the expansion too vigorous, destined to continue forever, leading to a big freeze where galaxies drift apart into an endless, cold, dark eternity? To answer this, astronomers needed to measure the history of cosmic expansion. They needed to look back in time to see if the universe's expansion was indeed slowing down as expected. The key was to find a reliable standard candle, an object of known intrinsic brightness that could be used to measure vast cosmic distances. Two competing international teams of astronomers embarked on this quest: the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Their chosen standard candle was a specific type of stellar explosion called a Type Ia supernova. These cataclysmic events occur when a white dwarf star in a binary system siphons off too much matter from its companion, exceeds a critical mass, and ignites in a thermonuclear detonation of unimaginable power. Because they all explode at precisely the same mass, they all release a nearly identical amount of light, blazing for a few weeks with the brilliance of billions of suns. They are cosmic lighthouses of a known wattage. By finding these supernovae in distant galaxies and measuring how faint they appear, astronomers could calculate their distance with unprecedented accuracy. And because the light from these distant explosions has taken billions of years to reach us, observing them is equivalent to looking deep into the past. The plan was simple: measure the distances to a set of these supernovae and, using their redshift, also measure how fast they were receding from us. This would allow the teams to plot the expansion rate of the universe at different points in its history. Everyone expected the data to show that the expansion was faster in the past and had been slowing down ever since, pulled back by the relentless tug of gravity. The teams worked for years, painstakingly scanning the skies, discovering dozens of these faint, distant explosions, and meticulously analyzing the data. Then, in 1998, a result emerged that was so shocking, so contrary to all expectations, that the scientists themselves initially refused to believe it. They checked for errors in their code, for biases in their observations, for any possible explanation, but the data was unequivocal. The most distant supernovae were consistently dimmer than they should have been. They were not just a little dimmer, they were significantly fainter, which meant they were significantly farther away than any existing model of the universe predicted. The only way for them to be that far away was if the expansion of the universe had not been slowing down at all. In fact, for the last 5 to 6 billion years, the expansion has been doing the opposite. It has been accelerating. The discovery was staggering. It was like throwing a set of keys up into the air and watching them, instead of slowing down and falling back, suddenly shoot upwards towards the ceiling with ever-increasing speed. Some unknown force, some form of anti-gravity, was at work on a cosmic scale, pushing the very fabric of space-time apart. This mysterious entity was given a name as enigmatic as its nature: dark energy. The revelation of an accelerating cosmos sent shockwaves through the scientific community. It implied that the universe was not just dominated by an unknown form of matter, but also by an even more mysterious form of energy. This wasn't just another puzzle piece. It overturned the entire chessboard. What could possibly be the source of this cosmic repulsion, this force that overwhelms the gravity of all the matter and dark matter in the universe combined? The most perplexing part of this discovery was that a potential answer had already existed for over 80 years, hidden within the equations of Albert Einstein's own theory of general relativity. When Einstein first formulated his theory in 1915, his equations predicted a dynamic universe, one that should either be expanding or contracting. However, the prevailing wisdom of the day was that the universe was eternal and static. To force his model to comply with this belief, Einstein reluctantly added a mathematical fudge factor to his equations, a term he called the cosmological constant. It represented the energy inherent in the vacuum of empty space itself, a kind of repulsive force that would precisely counteract gravity and keep the universe in perfect, static balance. A few years later, when Edwin Hubble presented his evidence that the universe was, in fact, expanding, Einstein famously renounced the cosmological constant, calling it the biggest blunder of his life. He had missed the chance to predict the expansion of the universe from his own theory. But with the 1998 discovery of cosmic acceleration, Einstein's blunder made a stunning comeback. Perhaps empty space itself is not truly empty. Perhaps it is imbued with a latent energy, a tension in the fabric of space-time that generates a persistent, outward push. This vacuum energy, represented by that same cosmological constant, would behave in a very strange way. As the universe expands and more space is created, more of this energy would come into existence, causing the expansion to accelerate even faster. It perfectly matched the observations. The leading candidate for dark energy was a ghost from Einstein's past. However, this solution comes with its own deep, unresolved problems. When physicists try to calculate the theoretical value of this vacuum energy from the principles of quantum mechanics, the number they get is grotesquely, astronomically larger than what we observe. It is a discrepancy of some 120 orders of magnitude, the single worst theoretical prediction in the history of physics. This chasm between theory and observation suggests we are missing something fundamental about the nature of space, time, and gravity. Alternative theories have been proposed. Perhaps dark energy is not a constant, but a dynamic field that changes over time, something cosmologists have dubbed quintessence. Or, perhaps more radically, maybe there is no dark energy at all, and the acceleration is a sign that Einstein's theory of general relativity itself breaks down on the largest cosmic scales. Whatever its true nature, this dark energy appears to be the most dominant force in the cosmos. When we now take a full accounting of the universe's contents, the picture that emerges is one of profound cosmic humility. The atoms that make up the stars, the planets, you and me, everything we have ever known or interacted with, constitute a paltry 5% of the cosmos. The invisible scaffolding of dark matter, the substance holding the galaxies together, makes up about 27%. And the vast, overwhelming majority, some 68% of the total energy density of the universe, is the enigmatic dark energy, the repulsive force driving the cosmic acceleration. We live our lives on a tiny island of familiarity, adrift in a vast, dark ocean of the unknown. For all of human history, we have been studying the 5%, mistaking it for the whole. It is as if we had spent centuries exploring a single continent on Earth, oblivious to the existence of the other continents and the vast oceans that separate them. The discovery of the dark universe is not the discovery of a new place. It is the revelation of the true nature of the place we have been all along. This realization forces us to reevaluate our position in the cosmos. We are not just made of stardust. We are made of the rarest kind of substance in the universe. Normal matter is the exception, not the rule. The fundamental architecture of reality is dictated by ingredients that are utterly alien to our experience, whose properties we are only beginning to fathom. The two great darknesses, dark matter and dark energy, appear to be locked in an eternal cosmic struggle. Dark matter, through its gravity, pulls things together, building the structures we see. Dark energy, through its repulsion, pushes things apart, seeking to isolate and disperse them. In the early universe, when everything was closer together, the density of dark matter was higher, and its attractive gravity was the winning force, allowing galaxies and clusters to form. But as the universe expanded, the dark matter became more dilute, while the strange, constant density of dark energy remained the same for every new cubic meter of space. About 5 billion years ago, a tipping point was reached. The repulsive push of dark energy finally overtook the gravitational pull of dark matter on the largest scales, and the era of acceleration began. The fate of our universe, the ultimate story of its end, now hinges entirely on the true nature of this dominant, dark energy. The future of everything now depends on the properties of a substance we cannot see and do not understand. If dark energy is indeed Einstein's cosmological constant, a fixed property of space itself, then our cosmos is destined for a future of majestic, cold isolation. The acceleration will continue unabated forever. Galaxies not already bound to us in our local group will eventually be pushed away faster than the speed of light. Not that they will break the cosmic speed limit, nothing can travel through space faster than light, but space itself will expand between us and them so rapidly that their light can never again reach us. One by one, the distant galaxies will recede from view, their light redshifted into oblivion. The night sky, for any observer in the far distant future, will become a barren, lonely place containing only the fading stars of our own merged Milky Way Andromeda galaxy. The evidence of the Big Bang, the cosmic microwave background, will be stretched to undetectable wavelengths. The evidence of other galaxies, of cosmic expansion itself, will be gone, pushed beyond our cosmic horizon. Future astronomers in this dark epoch will live in what appears to be a static, island universe, perhaps tragically unaware of the true, grand history of the cosmos. This slow decline into darkness and solitude is known as the Big Freeze, or the heat death of the universe. It is a future of endless, quiet decay into a cold, dark, and empty state. But there is another, more violent possibility. What if dark energy is not constant? What if its density is slowly increasing with time? This more speculative form of dark energy is known as phantom energy. If it exists, the cosmic acceleration would not just continue, it would become a runaway process. The consequences would be apocalyptic on a scale that defies imagination. This scenario is called the Big Rip. In the final stages of a universe dominated by phantom energy, the repulsive force would grow so strong that it would begin to overwhelm gravity not just between galaxies, but within them. First, galaxy clusters would be torn asunder. Then, the force would shred the galaxies themselves, unbinding the stars from their orbits and flinging them into the expanding void. As the end approaches, the force would become stronger still, powerful enough to overcome the gravity, holding our solar system together. Earth and the other planets would be ripped away from the sun. In the final moments, the force would overwhelm the electromagnetic forces that hold objects together. The Earth would explode. Then, in the last fraction of a second, the force would grow strong enough to overcome the strong nuclear force itself, tearing apart the very atoms and their nuclei. The fabric of reality would be ripped into its constituent, disconnected parts, leaving behind an infinite universe of nothingness. We stand at a unique moment in the history of thought. For the first time, we are aware of the sheer scale of our own ignorance. The darkness we have uncovered is not a void, but a presence. It is a tapestry of new physics, of undiscovered particles and unknown forces that have governed our universe from its inception and will dictate its ultimate destiny. The search for the nature of dark matter and dark energy is the primary driving force of cosmology and particle physics in the 21st century. It is a quest that takes us from the largest telescopes on remote mountaintops, mapping the shadows of dark matter on the cosmic web, to the deepest, quietest laboratories beneath the Earth's surface, listening for the faintest whisper of an ethereal particle. The challenges are immense, the mysteries are profound. But the drive to understand is a fundamental part of who we are. We look up at that same night sky that captivated Fritz Zwicky and Vera Rubin, but we see it with new eyes. We see not just the points of light, but the immense, invisible structures they trace. We feel not just the pull of gravity, but the inexplicable push of cosmic acceleration. The dark side of the universe is not an ending to our story of the cosmos. It is a dramatic, humbling, and exhilarating new beginning, inviting us to step out of the light of our familiar world and into the vast, uncharted reality that awaits.